Okay, hello everybody to today's lunch talk on thermal networks, challenges and outlook. My name is Tobias Sommer. I'm Senior Research Associate at Hochschule Lucerne. And within DeCarbCH, I'm leading work package 3 on technologies, design and operation of thermal grids for future energy planning. Before I start, I would like to show this picture that I took about 2 or 3 years ago in front of our university. You see a big trench here and blue pipes in the background. They were just putting pipes there for a thermal network that uses lake water. And the water is taken from Lake Lucerne and distributed to Horb and parts of Lucerne to supply buildings with heating and cooling. Then about, I think 2 or 3 days ago, I took another picture from the same perspective. The trench is gone, the pipes are in the ground, and the system is waiting to be operated. The structure of the talk, it has kind of 2 parts. And the first part is going to be about the decarbonization potential of thermal networks in Europe and in Switzerland. And the second part is about specific kind of new network designs for district heating and cooling networks. I would like to start with this quote here: heating and cooling are using almost 50% of final energy demand and are responsible for approximately 36% of CO2 emissions in the EU. That's a statement of the European Commission, and it kind of highlights the importance of heating and cooling regarding CO2 emissions. I would like to look at Switzerland now and the decarbonization potential of thermal networks in Switzerland. That's a very, very rough estimate, but for me it was important, excuse me, to kind of get the order of magnitude that thermal networks play in the role of play for decarbonizing Switzerland. Okay, the total emissions in Switzerland, these are 46 megatons at the moment. And the building sector produces 24% of this. That's about 11 megatons, mainly caused by fossil heating. Now, we want to bring these 11 megatons to zero by 2050. And the first step that has to be undertaken is insulation and refurbishment of the buildings so that the final energy demand for heating is reduced. The potential here is roughly about 30%. The different reports kind of deviate, but let's say we end up with 7.5 megatons there. And then the district heating, the thermal networks, they come into play. They might be able to reduce the CO2 emissions further down to 5 megatons by about another 30%. And then the remaining emissions should be reduced by individual solutions, so not thermal networks, just because the buildings might be too distant from each other, so that thermal networks are not feasible. Okay, using this very rough estimate, we see that thermal networks can reduce emissions by about 2.5 megatons. And if we relate this to the total emissions of 46 megatons, we end up with about 5%. So this is the order of magnitude, 5% decarbonization potential of thermal networks. All right. So now I would like to put Switzerland into an international, into a European context regarding the share of district heating on the final heating energy demand and the share of renewables within district heating. Okay. This is the share of district heating on the total demand for a few countries: China, Denmark, Germany, Poland, Switzerland, Japan, and the US. For Switzerland, here the share is given in this report to be about 6%. Actually, even current, this is a little bit older report from 2014, but even nowadays, 6% is sometimes cited. But according to Fernwärme Schweiz, it's more something like 9% at the moment. District heating should increase in the future, and there are reports saying that an increase by a factor 2 to 3 is realistic. So we are going upwards here. Okay, but that's kind of the comparison to other countries. We have Denmark at the forefront with 51%. We have Poland with a large fraction, but we'll see that, for example, Poland has a small share of renewables in district heating. That's the next slide. How much renewables are there in district heating? Switzerland is here. The 2014 estimate was 40%. And when I looked into this data a little bit more carefully and compared it to other reports, it's actually not so straightforward to quantify the share of renewable energy. Therefore, I would like to show this graphic here. The left column, this is the report. This is for the report that is shown here on the right side, the 40%. They quote a share of renewables in district heating of about 40%. And how do they get to this 40%? Well, it's clear that the fossil part, the black part here, that's not renewable. It's also clear that biomass, mainly wood, is renewable. And there are also other small renewable sources. But then there is this large fraction from waste incineration here in yellow. And what they did here is they just said they took basically the burned biomass into the renewables and the rest to the fossil part. That's how they end up with the 40% here. In Switzerland, waste heat from waste incineration is considered carbon neutral. So if you do this, you reach much larger fractions of renewables. But in this report, they just did it like this. So it's a little bit, you have to be careful when you quantify the share of renewables in district heating. Interesting is also that reports that state the production mix of district heating for the moment, 2019, 2020, they differ between each other. But for the future, it's clear that we should get rid of the fossil part. The waste heat part will still be, the waste incineration will still be a fraction of the total, but the other renewables, they will increase largely. Okay, so but for the international comparison, I kind of stick to the 40% for the moment. And what I did then, I plotted the share of renewables on one axis and the share on total demand on the y-axis, just to see where Switzerland is placed, roughly in a European context. The best would be to be here in the top right corner. Denmark, again, is at the forefront, but considering share of renewables, Switzerland is also performing quite well. And of course, we want to move that way, moving to a share of, if possible, 100% of renewables in district heating and increase the share on the total heating demand as well. So we need to build more networks, obviously. And this is only possible, I think, if we reduce the network temperature, because lots of heat, environmental heat and waste heat is available at lower temperatures. And therefore, we have to reduce the network temperature that we can actually make use of this low temperature, low temperature available heat sources. Okay, for this section, I would like to remember that a factor of 2 to 3 increase in district heating is realistic for Switzerland. More networks, of course, but also the temperature reduction aspect is sometimes forgotten and I think is quite important. This factor of 2 to 3 increase, this is a big motivation for myself to be active in the field of thermal networks, also within the DeCarbCH program in work package 3, technologies, design and operation of thermal grids for future energy planning. So from now on, I would like to move a little bit more to the technological part. And before doing this, I would like to show this slide here. I copied this from a presentation from Patrick Roost from EWL. He showed this at the Energieapero in Lucerne a couple of weeks ago, saying we are coming from a solar era, we are moving to a solar or a renewable era, and at the moment we are in this fossil peak time interval that we will overcome in the future, moving again to renewables. And I kind of like just the positive attitude of this picture, and I thought I'd show it here in the presentation. This figure is quite a famous figure. It shows the development of district heating, in particular regarding the network temperatures. So around 1900, district heating networks, they had really high network temperatures up to 200 degrees centigrade. And then the temperature was reduced down to almost ambient temperature now. And each temperature reduction was called a different generation of district heating, moving from the first to the 5th generation. And along with the temperature reduction, there is an increase in energy efficiency here in green. I would like to focus now for the rest of the talk on this 5th generation, what the authors call it. And it has certain characteristics. First of all, the sources, the plants that can be used for this kind of district heating, they can be very diverse. So you have many small inputs from solar thermal, geothermal, you have lake, river water, you have data centers that actually can put heat into the system. But you also have agents here in the system that can do both ways. So for example, just buildings, they need space heating in winter, but they can supply heat to the network due to their cooling demand. So it's kind of a more complex situation. And here for the characteristics, the authors claim there's heating and cooling supply. There's almost no thermal losses in the network because the network temperatures are so low. Sometimes the heat transfer across the pipes can actually have a positive effect. That's interesting. Uninsulated plastic pipes, and it should be very flexible and expandable, the system. Bidirectional. They call this system bidirectional. I think this is still an open question how you operate them, and we'll see that later on. Okay, this is a more realistic figure of how such a system could look like. So, for example, you have maybe some industrial waste heat as a heat source, but you might also have solar collectors. You have office buildings that have quite a high cooling demand in summer and heating demand in winter, individual houses, geothermal is there, and maybe you need some backup industry as well. So it kind of starts resembling an electric system where local producers of energy can actually supply energy to the network and also extract it. And Switzerland is actually at the forefront of this development of these thermal networks with really low temperatures. They are called Energienetze here, or the 5th generation of district heating and cooling. We see that here, compared to its size, Switzerland, in this report, they claim they have 15 networks. Denmark, for example, in this graphic, it doesn't show up at all. So there's really a chance that Switzerland can be at the forefront of this new development. Actually, counting the Energienetze in Switzerland at the moment, it's not 15, it's 23 at the moment. Okay. Now I'm getting into network designs. So we saw these networks, they are kind of complex. There's heating and cooling supply by various agents. How do you design such a network? And let's just assume for simplicity, we have 3 prosumers. 2 mainly have cooling demand and 1 has heating demand. These figures are motivated by a study that we did together with the University of Melbourne. So the cooling demand is actually higher than the heating demand there. But well, it also applies for the Swiss. The principles, they also apply for the Swiss situation. Okay, let's say there is a plant and 2 storages. So how do we connect them to the network? In the bidirectional network, there is a cold pipe and there is a warm pipe. Both of them are actually quite cold. So one could be maybe at 8 degrees, the other at 12 degrees. So both really cold with a temperature difference of 4 to 6 Kelvin, something like this. But one is warmer than the other. And the agents, they are connected in parallel to the network. And each agent has their own circulation pump. So for example, this prosumer here, he has heating demand. So he takes water from the warm pipe, extracts heat and injects it to the cold pipe. Of course, he needs a heat pump to actually reach the temperature levels needed for space heating domestic hot water. But the flow direction is from the right to the left here. Then we have a prosumer with cooling demand. He does it the other way round. He takes the cold water and injects it into the warm pipe. If the network temperature is low enough, that can be done directly using a heat exchanger only. If the network temperature is higher, a chiller might be needed. And now the interesting feature here is that the flow direction through the prosumers, it can be both ways. So also the flow direction across the storage can be both ways. And this has to be hydraulically solved typically. So if you use pumps like in the image here, they have to be controlled so that they can actually push the water both ways through the storage. And the goal is to keep the water flow through the bypass 0. But since control is never perfect with pipes in each agent, there is usually some residual flow, and therefore we actually need the bypass. So it's kind of a complex hydraulic setting. Before I discuss this, I would like to move on. Another idea is the reservoir network. In this network, there is a single pipe, the reservoir loop, and there is a pump that actually circulates the water through the reservoir loop. And then there are agents. They are now connected in series to the reservoir loop. And again, each agent has their own circulation pump. This is hydraulically very simple, but what you have to be aware of is that each agent injects water of different temperatures into this loop. So you have to control the temperatures. Kind of shifts the problem from the hydraulic side to the thermal side. But yeah, it's another option. And then, of course, there is the classical network. It's drawn in maybe a bit of an in a shape that's not that many of you might not be used to, but there is a plant, and the plant defines the volume flow, the mass flow in the network. There is a supply pipe, and there is a return pipe, and the agents are connected in parallel to these 2 pipes, and the mass flow is controlled by valves. That's basically the classical setting. Again, if you now have prosumers with heating and cooling demand, there is mixing occurring in the return pipe, which decreases the network efficiency a little. Right. So there are 3 design principles that are published at the moment that are known. In Switzerland, for example, ETH Henkelberg, Surstoffi Areal, FGZ in Zurich, they operate in the bidirectional way. Many lake water networks use the classical setting, and the reservoir network that has not been realized yet. Here at Hochschule Lucerne, we study the three systems in different ways. We have a lab here. On the left, the nodes lab, there we can actually run a little district heating and cooling network in the classical and in the bidirectional way, and do experiments, develop hardware for these systems. For the reservoir type, we use simulations. And in the last 5 years, we have published a number of articles comparing the different network designs. And if you're interested, you can look them up here. I would like to just very, very briefly summarize advantages and disadvantages of the different network types very briefly. As I said before, the bidirectional one is thermally the most efficient one. The heat pumps and also the circulation pumps, they actually operate most efficiently in this network simply because the warm and the cold water, they are separated. There's no mixing of warm and cold water occurring. However, the hydraulics, they are challenging due to the various pumps in the systems that operate in different directions. Then there is the reservoir network. This was actually developed based on, or resulted from the bidirectional network, thinking that we want to overcome the hydraulic challenges here. So the hydraulics of this reservoir network, they are really simple. The individual agents, they are hydraulically decoupled. For them, it feels as if they would take water from a reservoir, a lake or something, and put it back into the reservoir. That's where the name actually comes from. However, the temperatures might be challenging. And one important feature or interesting feature, I would say, is that here in this network, you only need one pipe, whereas in the other two network designs, you need two pipes, at least when you have a circular network arrangement. So you can actually save, this can actually cause savings using only one pipe. It has to be a slightly larger diameter, but in the end, there's savings. And then there is the classical network type. That's, as I said before, it's mainly used for lake water networks. One reason is that you actually, for lake water networks, you don't need storage because the lake itself, it's an ideal plant and storage at the same time. So that reduces the complexity of the network a little. All right. Summarizing the talk, I think it was important kind of to get an idea of the decarbonization potential of thermal networks in Switzerland. Order of magnitude estimate 5%. Then in the future, district heating is expected to increase by a factor of 2 to 3. Some reports even state 4 or slightly larger than 4, but most reports they are saying a factor of 2 to 3 is realistic and is needed to become CO2 neutral by 2050. And it's important that this goes along with a temperature reduction. If we build more networks, we need plants for these networks, and they are often available at low temperatures, so the network temperature should be reduced in the future. And then in the end, I showed 3 different network types, network designs that have advantages, disadvantages, and networks types that are used for these really low temperature networks, Energienetze, that can provide heating and cooling at the same time. In the very end, I would like to advertise a training course that we have here at Hochschule Lucerne starting next spring. It's called CAS Thermische Netze. And I'm teaching there the low temperature network part, but the program, it comprises much more. There's sections about material sciences, about planning, administration. Yeah, I think it's a very interesting course. It happened last year for the first time. And this year it's going to be the second time. So if you would like to register, there are links here on at the bottom of the page. And very last slide, if you are interested in existing thermal networks in Switzerland, you can simply open your browser and go to map-geo-admin, and there at the layer thermische Netze, and you will find a picture like this here on the left side, where all thermal networks in Switzerland show up, and you can also get the main characteristics of these networks. Okay, that's it from my side. Thank you very much for your attention.